Having developed a few iterative algorithms, we're now going to take a look at what are called recursive algorithms. So what are recursive algorithms? An iterative algorithm loops some sort of counter until a target value is reached. This is a typical way of doing it. A recursive algorithm, however, does something a bit different. So it refers back to itself. There's the word recursive. It refers to itself on a simpler set of inputs. And there will typically be some sort of designated output value for the simplest possible set of inputs. So for example, go back to sums. Okay. We're going to require all inputs to be natural numbers, but let's suppose that we can compute n minus 1 in addition to n plus 1, as long as I don't attempt to compute 0 minus 1. Okay, so we're only allowed to work with natural numbers, 0, 1, 2, 3, and so forth. And our built-in operations are not just adding 1, but also subtracting 1. Then we can define the sum of two natural numbers through the following algorithm. So here, notice, we start at a start, we input two natural numbers, I check if b is 0. Okay, I'm trying to compute a plus b. If b is 0, true, then I'm going to output a, because a plus b would be equal to a if b is 0. And then I would stop. But what if I'm not adding 0? Well, if b isn't 0, I can subtract 1 from it, and I can attempt to add a and b minus 1. Once I compute that sum, add 1 to that. We know this is going to be a plus b minus 1 plus 1. These will actually cancel out, and I will, in fact, be getting a plus b. But what we're doing is we're saying adding 0, that's easy. Adding something other than 0 can be reduced to attempting a different addition with an extra plus 1. So all we have to do is check, are we adding 0? If so, output a. If not, try to add a and a somewhat smaller number, but then add 1 to make up for the fact that this number had been made smaller. So what you have to do at this stage in the algorithm is basically pause the one that's currently running and start a new algorithm for this here. But this whole algorithm is the sum algorithm. So we start running through it and we pause it, and then we take this new set of inputs and try again. So here's that same algorithm, slightly smaller so that it gives a bit more space. Let's attempt to compute 3 plus 0. So we start because, hey, that's what we do. We input a is 3 and b is 0. And now we check, is b equal to 0? Well, yes, b was 0, so this is true. So I output a, which is 3, and I stop. Hooray, 3 plus 0, and we correctly output 3. What if I try to compute 3 plus 1? Well, we start, we input a is 3 and b is 1. Then I move here and I check, is b equal to 0? No, it is not, so I follow this false arrow. But that requires me to compute the sum of a and b minus 1. Well, b minus 1 is 0, a is still 3. So we're pausing the current computation of 3 plus 1 to start a new run of the same algorithm to try to compute 3 plus 0. So I go back here and I start, and now I input a is 3 and b is 0, because we're computing this sum here. Well, b is 0 is true, so I output 3. But this output was part of the first run. So now I'm going to have an output of 3 here, and I add 1 to that and output it and stop. So when I first tried to compute 3 plus 1, we had to pause that when we got here and say, well, let's now compute 3 plus 0, then add 1 to that before finally finishing. What if I attempt to compute 3 plus 2? So we start, we input a is 3 and b is 2. We check, is 2 equal to 0? No, it's not. Okay, so pause this version of the algorithm. And now what we have to do is start computing the sum of a, which was 3, and b minus 1, which is 1. So we're going to start the same algorithm over, but with a is 3 and b is 1. So we start it, we input a is 3 and b is 1. We check, is b equal to 0? No. So now we're back at this box again. So compute the sum of a and b minus 1. Well, a is still 3, but now b minus 1 is 0. Okay, start over. Start. Input a is 3, b is 0. Ah, now b is actually 0. So output 3 and stop this iteration of the algorithm. So here, when we were computing the sum of 3 and 1, we were called to actually compute the sum of 3 and 0, and now we know the answer for that is 3. So add 1 to that, to output 4 and stop. But that was computing the sum of 3 plus 1. Now that I know the sum of 3 plus 1 is 4, I get that in my original iteration to try to do 3 plus 2. Here I had to compute 3 plus 1. We now know that is 4, so add 1 to that to get 5 and stop. So the final output was 5. The fundamental result is the same as the iterative version. Okay, in the iterative version, we would have, to do 3 plus 2, done 3 plus 0, plus 1, plus 2, and counting them up one at a time. That's basically what we did here, but kind of in reverse. Instead of doing 3 plus 2, we say, well, can I do 3 plus 1? No. Can I do 3 plus 0? Yes, that's easy. So get a 3 and add 1 to it, get a 4 and add 1 to it, get 5. Basically, you do the same thing. You add 1 over and over again. How many times is this going to have to do a plus 1? As many times as I had to subtract 1 from b before this was finally true, until b had been reduced down to 0. So as I take 1 off of b until it reaches 0, I'm adding 1 here. I'm still adding 1 as many times as b requires. But the presentation of the algorithm just looks different, even though at the end of the day we went through the same steps. There's no loop anymore. The loop is essentially hidden. Rather than this loop of counting up as this counter variable, the loop is hidden by saying, here I'm starting to compute a sum, and then I pause it to compute another sum. And that might require me to pause that to compute another sum, and so forth and so forth. There's still kind of a loop, it's just hidden in the presentation of the algorithm. Let's talk about multiplication. Okay, here's a recursive multiplication algorithm. Input two natural numbers. If the second one is 0, well, a times 0 is definitely 0, so output that. If the second number wasn't 0, output a times b minus 1. We know from how math works that's going to be a times b minus a, so add a back to that to cancel it out to get the final result of a times b. So let's run through it with some test cases. Let's try to compute 3 times 0. We start, we input a is 3 and b is 0, and I check, is b 0? Yes. So I output 0 and I stop. Hooray. We correctly asked what's 3 times 0, and it says 0. Good job. What if I try to compute 3 times 2? Start, input a is 3, b is 2, ask, is b 0? No, because b was 2. So I go down here, and now I have to ask what's the product of a, which is 3, and b minus 1, which is 1. So I start computing that. Come back to the beginning, start, input a is 3 and b is 1. Is 1 equal to 0? It sure isn't. So come down here and try to compute the product of a and 0. 3 and 0. Back to the beginning, start, input a is 3, b is 0. Is b 0? Yes it is, hooray. Output 0. That was for computing the product of 3 times 0. Which was a step in computing 3 times 1. So now that I know 3 times 0 is 0, I can add 3 to it and output 3. Now that was for computing the product of 3 with 1, which was itself a single step in computing 3 times 2. So now that I know 3 times 1 is 3, add 3 to that and output 6, and finally stop. Basically, same process as the iterative version. We add a bunch of times, and there's some mechanism that counts how many times that has to be done. In the iterative algorithm, there was a counter variable I, and every time we added a, we increased that counter by 1, and once it reached b, we said, okay, now we've done it enough times. In this version, b is somehow tracking how many times we've multiplied a against itself, added a against itself. Okay, once I know I want a times 0, I know I want to output 0. Otherwise, try multiplying a with a smaller number and then adding a. Same basic process, we're going to subtract 1 a bunch of times until this is true. Then we run through this step as many times by adding a as we had to. How about exponentiation? Okay, we're just going through all of the same algorithms we developed iteratively in the last video, and now we're doing recursive versions. So to compute a to the b, we can start off by saying, well, a to the 0 is 1, and then just multiply by a. So here's a possible approach. Input two natural numbers that aren't both 0. If I want to raise something to the 0, output 1 and stop. If I'm not trying to raise it to the 0, raise it to a lower power but then multiply by a. This would compute a to the b minus 1. If I multiply it again by a, I will in fact get a to the b out. So let's try to compute 3 to the 0. We start, we input two numbers, they're not both 0. Great. Is b 0? Yes, it is. Output 1 and stop. In an attempt to compute 3 to the 0, we are output 1. That's good news. What if I try to compute 0 squared? So start, input two numbers, and they're not both 0. Good. Is 2 equal to 0? No, it isn't. So now I need to try to compute 0 to the first, which I will then multiply by a at the end. So I start, I input two numbers, a is 0, b is 1. They're not both 0. Great. Is b 0? Nope, that's false. So I come here and I start trying to compute a to the b minus 1. A was 0, b was 1, so now I have 0 and 0. That's an error. I cannot input both numbers being equal to 0. So somehow, this algorithm is kind of broken. When I attempted to compute 0 squared, we were ultimately asked to compute 0 to the 0. So a kludge is a sort of clumsy approach to fix a problem. Here's where we can do that. Input two numbers not both 0. A is the base and b is the exponent. If I compute 0 to any power, output 0. Otherwise, if I have something non-zero to the 0 power, output 1. If both of these numbers are not 0, then I'm going to do this same thing down here. So now let's try to compute 0 squared. This broke us last time. Start, input a is 0, b is 2. Is a 0? Yes, it is. So follow this arrow, simply output 0 and be done with it. What if I try to compute 3 squared? Start, not both 0. Is a 0? No. Is b 0? No. So now I'm going to try to compute 3 to the first power, and then when I compute that, I will multiply it by 3 again. So let's try computing 3 to the first. Start, a is 3, b is 1. A is not 0, b is not 0. So now I need to compute the same base a to one lower power, so 3 to the 0. Back to the beginning, start. A is 3, b is 0, a is not 0, but b is. So this is going to output 1. This is back in the computation of 3 to the first, is when this was first called upon. So now that I know this is 1, multiply it by a, 3, and stop that version of the algorithm. But that was a step in computing 3 squared. Now that I know 3 to the first is 3, multiply it by 3 and get 9 and stop. Okay, so this kind of weird combination of two separate checks, is the base 0, is the exponent 0, gets around the way the previous one failed. How about factorials? Well, the recursive version of computing factorials is pretty straightforward. The easiest factorial is 0 factorial equals 1. Otherwise, we use the fact that if you want to compute n factorial, you can compute n minus 1 factorial and multiply it by n. So go ahead and try to work through this for several different values of n to show that you correctly compute the value of, for example, 4 factorial, 3 factorial. Try 0 as well. The sort of special case is always one that's worth checking by hand. So pause the video now, try to work through a couple values and see if you get out the correct answers. Okay, hopefully you paused and checked this out. This is a pretty standard recursive version of the factorial algorithm. Again, notice there's no loop. At least there isn't one drawn on the page. The fact that the factorial algorithm calls upon the factorial algorithm is kind of hiding the fact that there's a loop there. Well, we've got iterative and we've got recursive algorithms. Why would I choose one form versus the other? Many people find iterative algorithms easier to execute. There's no pause this version of the algorithm to start running a new one. And if you're actually going through the algorithm by hand, it can be more straightforward to deal with loops and counting variables. But recursive algorithms are actually frequently easier to write. If you actually wrote codes for some of these, the recursive algorithms are phenomenally short. It would just be basically to compute the n factorial. If n is 0, output 1. If n isn't 0, compute n minus 1 factorial and multiply by n. You need about 4 lines of code, and that's it. Whereas the recursive version has this counter variable, and it has to iterate and increase the counter by 1. It requires more steps written down. So it's a longer program to write. recursive programming can be really, really elegant. Okay. Now we've included many computations for output blocks in these recursive algorithms. It's generally not the best practice for our purposes, but it does help highlight the recursive property. For example, we had blocks that said something like, compute the factorial of n minus 1 and then multiply by n, and we had this as a single block, rather than first do this and then multiply by n. Or do something like compute the product of a and b minus 1 and then add a onto it, rather than do this as one step and then do that as another. We were just kind of combining them to really clearly point out where the recursive step is. Okay, so as I mentioned, recursive algorithms tend to have really nice short code. And the computer can take care of all of the nested programs within programs, which are so hard to get through by hand. That does raise some actual computing power problems, however. Recursive algorithms can use a lot more memory than iterative ones because each call of the program has a sort of minimum amount of memory needed to execute. And if it starts calling upon itself millions and millions of times, that might be an issue. But that's a computer science problem related to specific environments that you're writing programs in, and different programming languages will handle this differently. And that's really beyond our scope. So we're going to attempt to present both styles whenever convenient. Here's an iterative version of this algorithm. Here's a recursive one. Some problems, however, one version is really going to be easier to work through than the other. In your personal development, you're free to focus on one versus the other. The point here is not a computer science class. The point is not you have to write these algorithms and code stuff. If one form is vastly preferable to you, that's okay. Try to work through them when we develop them, but when you have to do them on your own, if one of them is better, by all means, use that one for yourself. No big deal. But everything's going to be developed, everything's going to be presented to try to account for as many possible viewpoints as we can.